Okay, this video is to review some of the problems from exam number 1. Okay, so first of all, let's go through the multiple choice matching kind of problems that show up in the first part of the exam. Okay, so starting with number 1, quantity with only a magnitude. You check the list and you see item V is scalar. Okay, so that's the answer on this one. I think that one's pretty self-explanatory. Same thing with number 2. The metric prefix for 10 to the minus third, you look that up and you see milli. All right, so I'm expecting you to memorize, or at least have on a sheet. Memorizing would be better because you're training to be an engineer, but you need to know all the prefixes. Okay, next, in Excel, a reference cell that will change when copied or filled. That's relative addressing in Excel, so hopefully you'll remember that one. Okay, this comes from some of the Oakes and Leon reading, not knowing all the information. Excuse me. Not knowing all the information when developing a solution, item X. Okay, so there we have that one. And with Oakes and Leon, yes, you can still use your reading assignments that you did from that textbook to answer questions on the final or on subsequent exams. Okay, so number 5, the tendency of a force to cause rotation about an axis. I agree there's some ambiguity here. I think N and W. N is moment, all right, and W is torque. All right, both those are valid answers. Later on, you could eliminate one of those if, I think the problem said there's only one corresponding term. So you could have narrowed it down to just one answer, but, we'll go with it. All right, I give you credit for that. All right, revisiting steps in a process. Again, Oakes and Leon, that is iterating. Okay, a metric prefix for 10 to the 6th, that's mega, so which is item K. Process for finding a trend line from a set of data. Okay, so a trend line, there's different ways you can do trend lines. There's a linear regression. There's a way of doing an exponential fit, but all these are called regressions because it's a statistical term. You'll learn more about it as you go through the curriculum, but you should know that name. Okay, finding a trend line is the process of that is regression. Number 9, a coordinate system using magnitude and angle. Okay, that's the polar coordinate system. All right. Then we get to this, this 3-part thing that has one sentence. All right. So let me read through that and you'll see, what was intended here. I think I was pretty lenient on item 10 because it wasn't really clear. All right. So to calculate all right, so I look over here, moment. To calculate a moment, we find the perpendicular distance, okay, so perpendicular here, from the axis of rotation to the line of action, okay? So that's the definition of a moment, and that was the idea on 10 through 11. All right, next we get to some true-false. Unlike the scientific method, the engineering design process involves making decisions in pursuit of an open-ended solution. That is true. Okay, defining the problem is the 3rd step in the design process. Okay, so the implication here is this comes from the Oakes and Leon reading for design. All right, so if you see a problem like that, refer to your notes about that, and you can just look up the order of steps that were described there, and you can find that that's false. Okay, the technique for finding a line of best fit involves making sure the line passes through every data point. Okay, well, so we're referring to a linear regression here. And the points won't line up on a line, so that's the whole point of a regression is you find something that fits most of the data with less error. Okay, and so you'll never have them, if I sketched a picture here, all right, so here's a graph and I have data. It's seldom that the data lands right along the line, all right? You're just coming up with some fit that minimizes the error for the set of data. All right, so the answer on that one is false. Okay, so now moving on to 16, I do expect you to know what engineering notation is compared to, or especially compared to scientific notation. All right, so I expect you to know both, but engineering notation is the new thing from this course that you may not have seen before. I'm sure you've seen scientific notation before. All right, so notice here, I didn't really pay that much attention to significant digits. I feel like we've talked about this before. Significant digits can be overrated. I think it's important to know, but without having some context of where the number comes from, to me, it's hard to assess what is significant and what's not. So I didn't worry about significant digits when I graded this problem, and I won't on the final exam either, as long as you're reasonable about it. I don't expect, I wouldn't want to see 8 decimal points, all right? But you don't have to have it exactly right in terms of significant digits moving into the final. All right, so what you do is you enter this on your calculator, and you can calculate this in engineering notation. Certain calculators can give you that, so there you go, you got it, all right? But if your calculator won't do that, it might give you the answer in scientific notation. Okay, so what you need to do is use properties of exponentials to convert this exponent here to a multiple of 3. All right, and so the reason we do that is because this sets it up well for engineering prefixes. All right, 10 to the third, that's kilo. All right, so if this were measuring grams, and I had 11.2 times 10 to the third grams, I would be able to replace that and say this is 11.2 kilograms. Okay. So you get the idea on that. Okay, I'm going to erase this because that's a hypothetical that wasn't in the problem statement. Okay, same thing with the next part. You do this division, you get a number. All right, you make this turn into, using properties of exponentials, something you've done from high school, make that turn into a power of, or a multiple of 3, not a power of 3, a multiple of 3. All right, and so 10 to the minus 6 is micro. Okay. So there you go. It's really related to, engineering notation is related to the use of SI prefixes. All right, next. Okay, number 17. This is the last one we'll do with this video, and then we'll pick it up from here. All right, but next, one of the things that I want you to be able to do is to easily apply formulas that we've learned in this class. So the formula in this case is kinetic energy. Hopefully that's on your, in your notes. If I'm looking at a truck that's moving at a certain speed and I ask for the kinetic energy, it's 1/2 mv squared, all right? But the thing you need to be able to move forward with, and the things I think I saw the most problems on the exam with, were you have to use the correct set of units to make this work. And there's a couple of ways you could approach this. You could leave these in English units, okay, and apply the formula and then convert the final result into, clearly I'm wanting SI units here, okay? All the choices have SI units, okay? So somehow I've got to get from English to SI, all right? And so you could go all the calculations in English and then convert one last thing over to SI. My preference is to avoid the slug kind of calculation, because if you did this in English, you have to convert pounds mass to slugs, all right? And to me, I just try to, if I need it in metric, I'm going to just go ahead and convert it to metric. Okay, so that's what I did here. I converted pound mass into kilograms, and I just used that table that was included with the exam. Okay, same thing with velocity. I know that if I have an SI unit formula, I need mass to be in kilograms, and I need velocity to be in meters per second. Okay, so once I know those standard units, I can plug in here and get the answer. So I do these conversions. work this out, and then I plug that back into this equation, and I get 8.36 times 10 to the 6th. All right, so here I use this. I know that's meg, capital M. Okay, so megajoules, 8.4 megajoules is the answer on number 17. Okay, so hopefully that's helpful. Don't just, when you're going through this, don't just know how to do this one problem. Think about the general concept I'm trying to cover here. So the general concept on this one was convert a formula using the appropriate unit conversions. So you have to know what are the standard units that you put into a formula for the English system or for the metric system. Okay, so on English, the mass would be in slugs, all right, and the velocity would be in feet per second. All right, so if I'd given you this in miles per hour, you would have had to convert miles per hour to feet per second to use the English version of this formula. All right, so think about that, and you're trying to become a better engineer, so you're using these ideas and trying to bring those, deep into your psyche where you know what to do moving forward.